Hey guys, good afternoon. My name is David Dozier, and I am with our group. We're going to tackle the problem of the conservation of energy. So what that means is we're going to test and validate the idea that an object from a certain height has potential energy, but when it's dropped, that potential energy then turns to kinetic energy as it falls, kind of summing the two forces so that they're exactly equal throughout the experiment.
The conservation of mechanical energy is given by this equation here, which states that the change of potential energy plus the change of kinetic energy is equal to 0. Further expanding this equation, we can get this one right here. Now, the reason that the final potential energy is equal to 0 is because there's no height change when the ball is on the ground. And the reason that the kinetic energy initial is equal to 0 is because the ball is at rest right before we drop it. Further expanding this, we can get this equation right here, which states that 1/2 mv squared final is equal to mvh initial. Now we can prove this relationship by dropping the cue ball from different heights.
How we're going to do that is we built this nifty little tower. So how it works is it's got rulers, as you can see, at 4 foot, 3 foot, 2 foot, and 1 foot. What we're going to be doing is we're going to be dropping this cue ball. It has a mass of 0.17 kilograms or 6 ounces.
For this project, our group will be using the following assumptions when performing our experiment to demonstrate the conservation of mechanical energy. Number 1, our system consisting of a single mass and the Earth, the mass Earth system, is an isolated system, which means we are neglecting any and all outside forces from acting on our system, including friction, drag, and heat transfer. Number 2, by using the same cue ball for each trial as our mass, we are holding mass constant so that only varying heights will differ for each drop. Number 3, gravity is constant on Earth and in our system and is thus conserved. And if there are no non-conservative forces acting on or within the system, mechanical energy is conserved. Thus, the change in kinetic energy plus the change in potential energy must equal 0.
This table shows the average time it took for the cue ball to drop from each height. We dropped 20 times in 1 foot increments to calculate the average drop time. We then threw out 6 outliers and averaged the remaining 14 to get the final average drop time from each height. We then calculated the velocities shown on the right.
After doing the experiment and gathering all the data, these are the variables that we found that we're going to need to calculate KE and PE. This is the mass of the cue ball, this is the height, the initial height that we dropped it from, this is the average time it took to fall that height, this is the gravity constant, and this is the velocity formula that we're going to use to calculate the velocity right before impact, which we found to be 6.44 for a 1 foot fall. This is the formula we're going to use for kinetic energy, 1/2 mv squared. Once we plug in the mass of the cue ball and the velocity it took to fall 1 foot, we get a kinetic energy of 0.25 foot-pounds. This is the formula we're going to use for potential energy. Once we plug in the mass of the cue ball, the gravity constant, and the height of 1 foot, we get a potential energy of 0.39 foot-pounds.
After calculating the kinetic and potential energies for each height, we graphed our results and added a trend line and found an r-squared value of 0.97. If there is 0 error in our experiment, this r-squared value would be 1. Due to human errors, our r-squared value is less than 1, which results in our kinetic and potential energies slightly differing in values.
This applies to the real world through the basic principles of how a roller coaster works. When the cart is climbing to point A, it's gaining potential energy. At the maximum point A, the kinetic energy is 0 because the cart is not moving. When it starts to go down the ramp, the cart is gaining more kinetic energy and losing potential energy. At point B, the cart has the maximum speed, which means the maximum kinetic energy. The potential energy is close to 0.